So for those who joined, we'll start in 2 or 3 minutes. Okay, so let's start. Thanks everyone for joining us. We have Fong and Sudhakar, both are senior performance engineers at NVIDIA, and they're going to introduce to you the LLM task we have today, this year, first time. So we are ready. Whenever you're ready, Fong, share the presentation.
Thank you, Ovia. I can start now. Can everyone see my slides?
Yes, we see.
Okay, cool. Okay. Yeah, so hello everyone, and welcome to this year large language model task. My name is Phương, and my co-worker Sudhakar are very excited to introduce a new task this year, which is fine-tuning Llama 3.1 agent with LoRa. So a bit of introduction about us. So my name is Phương, and I'm a senior performance engineer at NVIDIA. Right now, I'm contributing to a library called Transformer Engine, where we provide a performance, mixed precision, accelerating transformer model training for a large language model on NVIDIA GPU. And prior to NVIDIA, I did a master in computational science and engineering from Technical University Munich, Germany. I was a former participant of student cluster competition at ISC-19, SC-19, and ASC-19. And just a funny fact, so I have lived in 5 countries in the last 9 years, so I hope that your cluster will be faster than my relocation plans. With that, I would like to introduce my co-worker, the second judge, Sudhakar.
Thanks, Fong.
Yeah.
Hello, everyone. My name is Sudhakar Singh, and I am a senior performance engineer at NVIDIA, the same team as Fong. I did my master's in CS from North Carolina State University. And as Fong already mentioned, we debug LLMs on NVIDIA GPUs for a living. And with that, we can get started with the introduction to what LLMs, the LoRa, and just try to demystify some of these things for you in as brief time as possible. So we'll start with pre-2017 era, where transformers were not a thing. We've had small RNNs, LSTMs, GRUs. They were the state of the art. And these models were still called language models. In 2017, Attention is All You Need paper came out, and it completely changed the landscape because it was the first time language models could scale beyond 1 GPUs. And language models started to become larger. in 2018, 2020, GPTs from OpenAI pioneered the causal decoder architectures that you see now. They had amazing generative abilities. And so language models started to be even larger. Now, a lot of stuff happened, but we will fast forward to 2023, 2025, the era that we are in. And we all know that how chatbots, they just took the world by storm. Then Meta open sourced their Llama series of models, 1, 2, 3, and now the latest ones. And they helped accelerate the large language model research in the open source arena. Remember, ChatGPT was OpenAI, and we could not get a lot of the details apart from just that it's a decoder causal architecture. But Llama made sure that even open source researchers had access to large language models with those weights that could be downloaded. And now you can see that we have a new paper every day. It's a breakneck pace. In fact, they can trigger geopolitical debates, as we saw in DeepSeek Carbon. With all of that, I still don't know whether the next phone call that I get is a scam or not. So there's still a lot of scope there. Next slide, please. Now, language models are trained over a long time and a lot of GPUs. And so we might wonder, if a language model is trained already, then is it good for everything? And we have figured out over time that a generic language model may not be good for specific tasks. So a generic language model can do very basic tasks like maybe machine translation, maybe helping answer some questions. But if, let's say, we want to build an e-commerce chatbot, and this chatbot needs to have very specific information about the products or the catalog that is on the e-commerce website, and we try to ask the question to this chatbot, it's probably going to hallucinate because it doesn't have the data. And so the solution is to train this pre-trained model with more data. And this data is very specific to the task at hand. And so on the screen in the slide, you can see that there is a pre-trained model. Imagine that to get to this pre-trained model, we spend a lot of GPU and compute and time. But now it goes through further training, and we call it fine-tuning. And this fine-tuning can be supervised. And as you can see in the diagram, we have two ways to supervise it. For example, summarize the following text. And then you have a text and its example completion. That's one way to supervise. The other way is translate this sentence. So there is an example text and there is an example translation. Sorry, there is a typo there. So with a lot of these prompts and completions, now the model learns or fine-tunes its weights or adjusts its weights for this very specific task that we have. And so fine-tuning makes a model polished for the specific task that we have. Next slide, please. There are a few ways to do fine-tuning, but one of the ways which shown in the past few years has been low rank adaptation technique, and I'll talk you through why it is the case. According to the original LoRa paper, it can reduce trainable parameters by 10,000x. Now, let's take a look at why this is the case. When I told you about fine-tuning a language model these days, for example, the one that we have for this specific task is 8 billion parameters. And if you want to fine-tune it, do you want to adjust all the weights in the model? Earlier, we used to do this, but over time, we realized we don't need to do that. We can add a few weights to the model and then only train or fine-tune those. And then later, we realized that we don't need to, or we can actually have very small set of weights that can replace those larger weights that we want to fine tune. And that is the low rank decomposition of a matrix, of a weight matrix. And that's how we are able to only select a few layers in an entire 8 billion model and only train or fine tune the parameters for those layers. And that's how we are able to reduce the trainable parameters by such a huge amount. And in this slide, we can see how the fine tuning happens, or the comparison between a regular or basic fine tuning, in which we fine tune or adjust the base weights. And on the right-hand side, there is a LoRa adaptation. Let's dig a bit deeper into this. On the left-hand side, you can see that we have a single trainable weight, which is 1024 by 1024. And in the forward pass, of course, the flow of information happens in the from inputs to outputs or to activations. And in the backward pass, the gradients flow from activations through the weights and to the inputs. Now, when the gradients flow through the weights, there is also an adjustment made to the weights, which is the weight update. This has been the regular fine tuning for a lot of time, but on the right-hand side with LoRa, what ends up happening is we take a low-rank decomposed weights corresponding to a weights layer, a base weights layer, which is the blue one on the diagram. And what ends up happening is that we freeze the base weights, and we have trainable LoRa weights. In the forward pass, we pass the information through both of these paths, and we combine that to get the activations. Now, in the backward pass, although the information flows through both the paths, but since we froze the base weights, only the LoRa weights are updated. And at the end of this fine-tuning process, we can just add those weights, and that is all. So what ends up happening is, since we have a small subset of weights that we fine-tune, the fine-tuning is faster. And secondly, when we deploy it, we can keep the base weights in the memory, and we can just swap in and out the LoRa weights. And that's how you can have maybe different type of agents in a single system, and you can just play around with different configurations. You just download the adapter instead of downloading the entire model. And that is how LoRa fine-tuning helps us get to fine-tuning models faster and then storing the LoRa weights in a much smaller memory footprint. And with that, I would like to give control to Fong for the rest of the presentation. You're on mute, Fong.
All right, I'm back. Yeah, so I wanted to say thanks to Sudhakar for a great overview on what is LoRa fine-tuning. And with that, I would like to give some information about what do we have for the competition, what do we expect, and what can you play around with. So for the competition, we have two benchmarks. The first benchmark is the speed benchmark. And for this one, with the fine-tuning, your goal is to achieve the highest train sample per second during the fine-tuning process on a given train data set. So here, of course, you have a lot of freedom to do whatever optimization that you believe is good for speed. And the only requirement is that you need to run at least one iteration or one epoch, and the result should be reproducible on the same hardware. And after you explore different optimization technique, you are happy with the speed benchmark, then you can take the fine-tune model and perform the accuracy benchmark. In the accuracy benchmark, the goal is to achieve the highest accuracy on the evaluation dataset. So the only requirement here is that you need to provide the checkpoint so that we can verify your submission afterward. So even though you see that we have two benchmarks at a separate criteria, these two benchmarks are highly tied to each other. Whatever you do for the optimization for the speed benchmark, it may affect to the accuracy, either in the enhancement way or in the worst way. So we recommend you to play around and see like how different technique of optimization can improve or making things worse for both speed and accuracy benchmark, and then make the decision by your own which one is the best you want to keep for the final competition. And with that, we have a short report in the evaluation as well, where we want to see how do you decide that which optimization technique that you have tried, and if you decide to use it for the final competition, why, and if you see any trade-off when you do different optimization, whether the speed is higher but the accuracy is worse, or the speed is lower but the accuracy increased. So we want to see a short discussion in the report, and of course you also can provide what you have tried and failed. That is our favorite part, because it tells others that you have been there and don't do that, right? Been there, don't do that. Yeah, and the report, the shorter the better. So that don't need to try to maximize the number of words here. We provide you a reference implementation on the GitHub repo, and here I can give you a brief overview of the code structure. So we provided a report template, even though you don't need to follow this, but having a look like what you we expect here is also a good starting point. We have the config.py file where we define all the LoRa parameter and all the parameter for the trainer. So please have a look, and you can play around with this parameter accordingly. The main.py mainly for calling different components in the Pythoning pipeline, and also logging. For the requirement, this is the place where we put all the packet or the pip packet that we need for the file tuning. So if you have any extension, if you use any extension in additional, then please put them here so that we can reproduce, can install them when we need to reproduce your output. We have a run script where you can see how to start the accuracy or the speed benchmark. And overall, we have a source code file. So here I can, on the right side, you can see different components of the fine tuning pipeline. So we have a data loader that is implemented in the dataset.py. So here we the data loader loads the input and also do all the pre-processing that it needs to do via the prompt config that defined in the config.py. And after the pre-processing the input, it returns a list of input, and the data collator is the one that batching the input into batch before fitting into the trainer. So for the model, we define the model in the LoRa underscore model.py file, which consists of two parts. The first part is the original model where we take the Llama 3.1 in BF16, which were downloaded from Hugging Face, and we load it into the program. And the second part is we have a LoRa weight where it initializes all the LoRa weight that it needs according to the config that's specified in the config file. And we combine, if you remember from Sudhakar previous slide here, so we keep both of the original weight and the LoRa weight in the model for the trainer, but in the training, we only update the LoRa weight. So after we have a model, we can grab different parallelism layer on the model, and this is defined inside the distributed.py. So here we provided the reference implementation for distributed data parallelism, but you are free to implement and explore more and order parallelism and have a new implementation in this file. So the trainer do the fine tuning job and eventually also checkpoint the LoRa weight in B float 16. So here I also highlight that here we believe that if you need to do any optimization or you want to play around, LoRa model and the trainer and the parallelism are four different parts that you can play around, implement your own part or your own optimization. For the rest, we believe that it should be kept because they're not directly related to your optimization, and we want to give some code structure so that we can do the evaluation later. So we provide you two data set for practicing at home. The first data set is the Cosmos QA. So it consists of 35K multiple choice question, and mostly it relates to the model need to read some context and then need to really think about what is the cause and the effect of the event to be able to come up with the answer. And for the evaluation, it's quite similar, and that we also have a multiple choice question. But here the model really need to learn from the past, and then here need to read the context and understanding the context, and also have additional reasoning to be able to come up with correct answer. So this data set actually have both image and text only questions, so we exclude the image related question. So I think the result data set is around like 5K text only question that we use for evaluation here. So at the competition, we will prepare you guys a two new secret data set. You cannot say much because it's secret, right? But the only thing you should know that is that it will be multiple choice and it will be text only, so that it still work with the current prompt config and also data loader and evaluation. So there are so many optimization techniques that you can play around. Here we just lay out a few optimization that we think that may be relevant. But you are free to try all the optimization as well. So the first optimization that we suggest you to try is that you can play around with the LoRa config. So in the reference implementation, we only apply LoRa to QKV and the output layer of it in the attention part. So you can try to apply LoRa to all the layers and see how the speed and accuracy change. You also can adjust the LoRa parameter, how large the LoRa weight should be, and then find different combination to apply to different layers. In addition, you may be interested in quantization and fine-tuning in lower precision, like 8-bit or 4-bit. So we encourage you to try and see how it affects your speed and accuracy. As I mentioned, inside the reference implementation, we only implement the DTP with the distributed data parallel. But you are free to try all the parallelism technique and see if it benefits your fine-tuning at all. And any other Python-based extension like deep speed, fast attention, and so on are welcome, provided you documented them. Again, we just want to remind you a few constraints we have here. So first, we want to have PyTorch as the base framework. So whatever you implement, it should be based on PyTorch, and also whatever extension that you use, it should be compatible with PyTorch. You should keep the code structure as provided, as well as all the checkpoint and logging, so that we can reproduce your result, as well as we can have the evaluation smoothly, going smoothly. And all the result you report should be reproducible, meaning that for the speed benchmark, the result should be reproducible on the same hardware. And for the accuracy benchmark, we will take your checkpointed LoRa weight and combine with the original model weight, and we will run our own evaluation on our hardware. So we expect it to be at least approximately similar to the result that you have reported. And for the submission, you can use the same repo as we provide with some additional file. So here we especially interested in the final model checkpoint with the index model.pt. So here we only checkpoint the LoRa weight, because we will take this LoRa weight, we combine with original model for our own evaluation. So please include any source code if you have any code modification, any code optimization, and also please have a configuration file where you change any parameter and also a run script. If you don't have anything, change anything in the run script, then you don't need to include this. And in addition, we want 2 more files. That is first is the std out, the output when you run the speed benchmark. So please copy or redirect them into a file, and the same for the accuracy. And together, please put them in a folder and zip them with the following name before the submission. So I think at the competition, Ophir will give all the team a USB stick. So please copy everything and put it into a file and submit your result accordingly. So with this, thank you, and we're really excited and looking forward for your performance at the competition, and looking forward to see all the technique that you try for optimizing this fine tuning, and let us know if you have any question.
Thank you, Fung. If anyone has any question, just feel free to ask. In any case, we are also, on the Slack. So if you get questions later on, just you can ask it in the Teams group, the Teams channel, or the main channel. Anything, just feel free to contact us. We'll try to help with any issues that you have, any questions that you encounter. No questions? Everything is understood? That's good. You see, it was easy. You see, we should be harder on them. Okay. So I would like to thank Fung and Sudhakar. Thanks for the presentation, and see you all in Hamburg. Okay. And I'm going to I record that, so I'll send the link later on. Okay. Okay. So bye everyone.
Thank you. Bye.
Thank you.